So please enter your attendance now. If you enter your attendance before I join the Zoom session, you should re-enter it again. So the syllabus for your CAT 1 is still curvilinear coordinates, the topic that we covered last week. So you go through the materials provided to you and the lecture video also. But today I'm going to start tensor analysis. So it'll be just probably a very short and a very brief class. It'll be introduction of tensor only. I am not going into details of tensor now because this is something we need to cover after your CAT 1. Just 1 minute. I have to make it large. Come on. Yeah, slide so. So in this tensor analysis section of Unit 3, we are going to cover this brief idea of tensors and the transformation of coordinates, summation convention, and all these things. Okay. Now, let us give a brief introduction of tensor today. We know that whatever we know in physics so far is we know there are certain quantities like physical quantities. All physical quantities we have encountered so far, we can classify them into what is called scalars and vectors. So any physical quantities that we have encountered so far, we can classify them into scalars or vectors. Like for example, temperature or energy, they have a magnitude. That kind of physical quantity has a magnitude, but they don't have any specific direction. So such quantities, we classify them under scalars. And uh, other quantities like force, velocity, position vector, and all those things, we know that in addition to having a magnitude, they also have a specific direction. So having direction, those physical quantities having directions, we classify them as vectors. But like if we get into like more details, uh, particularly in analyzing the material property and also in three-dimensional space, there are certain physical quantities that cannot be clubbed under scalars or vectors. So what I mean to say is that the concept of scalars and vectors is no longer sufficient to categorize or to to identify such kind of physical problems, such kind of physical quantities. Like for example, this is one example that I often give as an introduction to this tensor analysis. Here, Ohm's law simply says that voltage is equal to V equal to IR, right? V equal to IR, and you know, resistance of the material is equal to resistivity, uh, and it is directly proportional to length, inversely proportional to cross-sectional area. What is that? Yeah, something like this, if I remember it correctly. Directly proportional to length. So if the length increases, this thing, the resistance of a material increases. If the cross-sectional area increases, the resistance of material decreases. Yeah, something like this. So if you put all these things together here, resistivity and all, and you know that conductivity is reciprocal of resistivity here. So current here, current density J is actually current per unit cross-sectional area. So current per unit cross-sectional area. Considering all these things, you can rewrite this Ohm's law into this. So when we write Ohm's law into this, we have a relation between, voltage is directly proportional to electric field, right? Voltage is directly proportional to electric field, and voltage is actually electric field into certain length. Okay, so if you substitute all these things, this is what you're going to get. And this current density, electric current density, current per unit cross-sectional area, it's having a certain direction of flow of current. So that means it's having it's a vector quantity, and electric field is also a vector quantity. And uh, here, this relation between J and E here, according to this relation, it simply states that if we write in terms of 3D Cartesian, current density can be expressed in 3D Cartesian system as Jx I cap. I cap is unit vector along x, j cap unit vector along y, k cap unit vector along uh, z. So Jx is component of current density along I x axis. Jy is component of current density along y axis, and similarly Jz is component of current density along the z axis. And similarly, the electric field can be resolved into these three components, can be written in terms of the components in three-dimensional space, 3D Cartesian space. So if we write in terms of that, what this relation here simply means is that sigma is the conductivity here, means that uh, here, if you're going to write like this, Jx, the component of this current density along x is equal to sigma into Ex. So if you substitute this here, this is what you're going to get. Jy will be equal to sigma Ey, Jz is equal to sigma Ez. So this relation here, it holds only for isotropic materials. Isotropic materials in a sense are those materials which do not have any preferential direction. That means if you apply electric field along x-axis, it will cause electrical conductivity along x-axis uh, uh, only. It will not, suppose your electric field is given by Ex I cap only. So if there are no electric field component along y and z axis, then if you're going to write in terms of this relation here, what we are going to get is Jx I cap plus Jy, J cap plus Jz, K cap equal to sigma Ex I cap. So on the right hand side, the J component is 0, K component is 0. So what we are going to have is current along the x-axis. We are not going to have any current along the y-axis. We are not going to have any current along the z-axis. So this linear relation between current density and the electric field here shows that this conductivity is a scalar quantity here. And if this conductivity is a scalar quantity, then whichever direction you are applying electric field, you will have a current in the direction only. You don't have a current in other directions. That is in the case of isotropic crystals. But in certain anisotropic anisotropic crystals or anisotropic medium, or in outer space, in a plasma atmosphere, uh, this J and E uh, are no longer relation between J and E are no longer governed by this linear relation or Ohm's law. What I mean here is that this is no longer governed by this, means if you apply electric field along x-axis only, then current component along y-axis and current component along the z-axis does not necessarily become zero. So in an isotropic medium, it now has a preferential direction, or this uh, scalar relation, linearity relation no longer holds. So what happened is that in such material medium, anisotropic medium, anisotropic crystals or a plasma medium, the relation between the component of J, like here I simply represent Jx as J1 and Jy as J2 and Jz as J3, and similarly if I represent Ex as E1, EY as E2 and Ez as E3. So if we do that, this is now the general relation between this current density and the electric field. And uh, here, what we can see here is that if you have electric field along, let's say, x-axis only, if the electric field is applied along x-axis, Ex I cap, or Ex, we write it as E1 means E1 I cap. If I write it like this, then you know that here, if the electric field is along the applied along this thing, that means E is along E1 I cap, E is equal to E1 I cap, then that means your E2 is 0, your E3 is 0. Even if that is the case, you will have current along the x-axis. J1 is Jx, right? You will have current along the x-axis J1 as sigma 1 1 E1, and J2 is no longer 0. So what we are going to have it as a J2 current along the y-axis is, you know, here you see that the current is, the electric field applied is along the x-axis E1. So E1 is there. So E2 is 0, E3 is 0, right? So your J2 is also sigma 2 1 E1. And your J3 is also sigma 3 1 E1. So in such anisotropic medium, we cannot say that J2 and J3 will be 0, right? In isotropic medium like this, when this relation holds, that is when the conductivity is scalar quantity. If you apply electric field along x-axis only, then you will not have any current along the y and z axis. But in an isotropic medium or a plasma medium, uh, uh, the property of this current density and the electric field, that is the Ohm's law, is no longer valid. It's going to be defined by this relation. So in general, we can write this as we can write this as sigma, the conductivity, as a tensor, what is called another quantity classified as a tensor. So this conductivity sigma, uh, though it in isotropic medium, it is a scalar quantity, but in anisotropic medium, we can no longer classify this conductivity as a scalar quantity. So beyond the scope of these vectors and scalars, we define another what is that classification of physical quantities called tensor. So tensor is simply a mathematical concept of representing this kind of physical quantities which cannot be classified under scalar or vector. Okay, which cannot be classified under scalar or vector. So do not think it as a certain entirely physical entirely something what is that concept which is uh, difficult to understand or like that, but just consider this tensor representation as a mathematical tools for representing certain physical quantities which cannot be classified under or represented as under vector or scalar. So this no longer is a scalar. Sigma is no longer a scalar. It's no longer a vector. It's not a vector also. So it's a tensor. So when this becomes a tensor, it is the general relation between the electric field and the magnetic field. So if this is a isotropic medium, in isotropic medium, what we are going to have is sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 3, sigma 3 1, sigma 3 2. They are all zero in isotropic medium. But in anisotropic or plasma medium, they may not necessarily be zero. Okay, so this is called a conductivity tensor of the medium, conductivity, electrical conductivity tensor of the medium. uh, I'm taking this class just for the sake of this thing, taking the class because I feel that I should not continue too much on this tensor, because you're going to have your cut exam from day after tomorrow, right? So it will be a certain long gap, because we are not going to have any continuation of this class, nor a continuation of uh, whatever we are going to do later on. So I think I will stop, because I don't think you will be in a mood for a new topic. And I will stop here. But if you have any question in any of the topics that we covered so far for your Cat 1, please feel free to ask. We have started with vector analysis, and we introduced those del, gradient, scalars, gradient divergence in Cal and all. And then we covered what is that vector integral theorem, like Gauss divergence theorem, uh, Green's theorem, and Stokes theorem. And then we also finished this curvilinear coordinates. So tell me if you have any question regarding the topics that will be for your Cat 1. Anything, if you have started preparing for your Cat 1, let me know, because we are going to need only 4 or 5 lectures to cover those tensor analysis. So we don't have much. We don't need much more lectures to finish our syllabus. So I think we can utilize this time for uh, any queries if you have. Okay, if you don't have, then all the best for your Cat 1. Then after Cat 1, we can finish this tensor analysis in 5 lectures, most likely. Okay, I'll stop then.